Okay, so now let's discuss the next application, which is the discharging of an open tank. We already solved a problem like this a couple of videos ago, where we had a tank and the tank was discharging, and we wanted to see how much velocity of the fluid that's leaving the tank. So we're going to do similar thing, but from a different perspective. So um, we know that the container or a tank that has an open surface will be exposed to the atmosphere, and if it's a large tank or a big tank that has big diameter compared to the diameter here, then the velocity here will be so very small compared to the velocity at the discharge. So we can consider the velocity here to be zero. So we said we can apply Bernoulli equation between the 2 points, between point 1 on the surface, point 2 at the discharge. Point 2 is at the atmosphere, point 1 is the atmosphere. So both are atmospheric pressures. We know the height here will be 0, the height here will be h, and uh, we can calculate or get u2 as a function of h. So it's going to be square root 2gh. This equation is a famous equation. It's called Torricelli equation. And Torricelli equation is telling us a lot about the discharging of fluids from open tanks, because it tells us that the velocity will decrease as the height decreases. So as in the beginning the height is high, so the velocity is high, and as the height decreases, the velocity will decrease, and it will keep decreasing, and the tank will keep discharging until all the fluid above the opening is fully discharged. So the flow will stop when the liquid height is here. Okay, which is logical and expected. Now let's try something else, and this is a modification to the equation. Or to the case that if you have a tank that's discharging, but it's a closed tank instead of being an open tank, meaning that the tank is sealed. There is no, it's not open to the atmosphere. So when the apply the same principle on the tank in the beginning, the pressure here is atmospheric and the outside is atmospheric. So in the beginning they will behave in the same way. But as we discharge, the liquid discharges, the height of the liquid will decrease, and the pressure inside the tank of the air inside the tank will decrease. And it will decrease because the tank is not open, so the same number of moles occupy larger volume. And if you assume that's an ideal gas, PV equals nRT, so as the volume increases, the pressure will decrease. So it's very expected. So as the pressure decreases, this will make some changes in the equation. So in the beginning, it will be the same shape that we are used to. Now, if you apply an ideal gas law, as we said, P is directly inversely proportional to the volume. So as the volume of the gas increases, the pressure will decrease, while the pressure here is constant. It's atmospheric. So we can write the Bernoulli equation again, but in this case, we cannot cancel P1 and P2. So we will keep P2 as atmospheric pressure and P1 as P1. Okay, so now the equation differs. If P1 is atmospheric pressure, we will go back to this equation. But if it's not, then it will be the different thing. Now, if we look at this equation, you will notice something that is interesting. The velocity can be zero while z1 is not zero. What I mean is that there is a negative term here. So this negative term will cause the whole terms under the whole value under the root to be zero when z1 is not zero, which means that the velocity will be zero while the fluid is still above the opening. So you'll have the water level above the opening already there, and the fluid is not flowing outside, which is an interesting thing. And if you put U2 equals 0, you can get a relation between Z1 and the P1 minus P atmospheric minus P1 over rho G. Okay, so this is an interesting thing. So I already did this at home, and it was a simple but an interesting experiment. So I did this for a small container. where I have that this is open to the atmosphere, and there is a small hole that I drilled here, and I left it to discharge, and you see it was going slowly, and I sped it a lot because it was very very slow, and you see it's getting slower and slower as it goes down, and this is what we already mentioned before, that as the height decreases, the velocity will decrease. Uh, but the point is, it kept discharging until it reached the opening. Now I did the same thing for a closed tank, and it's the same tank, but I have the cap and it's discharging as it did in the beginning, and I am closing the container now. And once I closed it, it stopped. So this is a very, very interesting thing, and you'll find a lot of videos on the internet about people made about using this phenomena for um, uh, for instance, if you have and you're in a camp or something, and you want to you have a limited amount of water, and you want to make a tap for yourself to pour water. So one thing is to make something like this. You have a container and you have the cap, and you open the cap so that water can come out. You wash your hands and then you close the cap, and it's done. So it has a lot of things. There is one other thing that is a video about what's called the assassin's teapot. So it's an interesting thing actually. And I'll put the I say here on Blackboard because I posted for my students, but I'll put the link to this video in the description of the video. It's an interesting thing. It's one teapot that was used for people a long time ago for yani, putting something for them to drink that's poisonous. So they have a teapot that has two compartments, and they can control which, and each compartment contains a fluid. One is dangerous fluid or the poisonous fluid, and the other is not. So they can pour from the same teapot two different fluids by closing a secret opening like this. So it's an interesting thing. I'll post the video, and you can watch it later. So anyway, so this is the what I have here. I'll stop here, and next video we will discuss one more application, which is liquid siphoning. So I'll see you then.